Okay, so this is going to be a continuation of Haluk's talks. So he told you about the cohomology of SL2Z, then moved to Bianchi groups, and told you a little bit about SL2 of the ring of integers of other number fields. And here we're going to generalize this a bit more to go to the realm of Quaternion algebras. And so that's going to be more examples of arithmetic groups in the sense that Paul told you a bit about yesterday. So hopefully some concrete examples. And we will mostly focus on the three-dimensional case because there's already quite a lot of interesting things going on there. So the talk will be first some definitions and setup, and then some algorithmic parts. So that will be the first lecture. And the second lecture will be a bit more about some theoretical aspects and conjectures in that setting. Okay, so let's start. So first, I'm going to give a few definitions of what these Quaternion algebras are. And the associated arithmetic groups. Okay, so the basic definition is as follows. You take K field, and I'm going to assume that it doesn't have characteristic 2. And so a Quaternion algebra is an algebra of the following form. Denoted by A. It's generated, it has basis of 4 elements. As following relations, I squared equals A, J squared equals B, for some A and B that you choose as non-zero elements of the field. And the extra relation between I and J is that they anti-commute. That completely defines the multiplication in this algebra. And, well, for this, I will use the notation. I will write this as A comma B over K, just as a shortcut for that definition. Okay. Just some basic examples. If you take A equals B equals 1, this is actually isomorphic to the 2x2 matrix algebra over K. And you can check that this map actually works as an isomorphism. I leave this as an exercise to check that this is an isomorphism of algebras. Another classical example is the algebra where you take -1 over the reals. This is famously a division algebra. And so this is Newton's Quaternion algebra. Okay, maybe one example of a simple isomorphism between Quaternion algebras that you can have. If you replace, if you multiply A and B by non-zero squares in K, then this doesn't change the algebra up to isomorphism. I just send here I to Ui j to Vj. So yeah, here. So U and V star. And so in particular, if K is an algebraically closed field, for instance C, then you can take out everything into a square, like A and B, and get 1, 1. And so every quaternion algebra over an algebraically closed field is isomorphic to M2 of K. Okay. Oh, yeah, I should say, please feel free to ask any questions at any time. I'm happy to answer questions. Okay. Some extra basic definitions of operations that you do on quaternion algebras. So a basic operation is conjugation, meaning a map from A, the map from A to A, which we will write something goes to something bar, defined by, well, so it should be K-linear, and send I to minus I, J to minus J, Ij to minus Ij. And the important property of this is that it's an anti-automorphism of the algebra. So if you conjugate product, you get the product of the conjugates, but with the order reversed. That's easy to check from the definition. And from this conjugation, we can make two extra definitions, namely the reduced trace, which I will denote TRD of W. That's just W plus W bar. And that actually belongs to K. That's also easy to check. And so that defines a K-linear map from A to K. And more interesting one is the multiplicative one, the reduced norm. There should be minus here, sorry. Yes. All the imaginary ones, you the minus sign. Yes, sorry. And so, yeah, the reduced norm is W times W bar. And again, you can check easily that this belongs to K. And the important thing is that the reduced norm from A to K is multiplicative. Okay. Yeah, reduced trace, reduced norm. Okay, so some more examples of this. When you transfer the reduced trace and reduced norm to the 2x2 matrix algebra, you just get the usual trace and determinant. So this 1, 1K is morphic to M2 K. So you can transport reduced trace via this isomorphism. You just get the usual trace of matrices, and reduced norm, you just get the determinant. So that's that. And the final basic property of quaternion algebras that I want to mention is the following. Well, okay, maybe something else I should say about the reduced norm is that so because of the relation, so W bar equals reduced norm W for WA. This implies that W is invertible if and only if the reduced norm is non-zero. And in that case, well, W inverse is just 1 over the reduced norm times W bar. So in that sense, reduced norm detects invertibility. Okay, and so yeah, one basic property that I want to mention is that if you have a Quaternion algebra, then there's only two things that can happen. Then either A is isomorphic to the 2x2 matrix algebra, or A is a division algebra. Okay, maybe I should, yeah. Divisional algebra, is that okay for everyone? I mean, okay, I'll just put the definition. So divisional algebra just means every non-zero element is invertible. Just to be sure everyone understands this. Okay, so there's only two things that can happen, either divisional algebra, like, for instance, the Hamiltonians, or the 2x2 matrix algebra. Okay, any questions so far?
I'm a little bit confused.
Yes.
How the norm is multiplicative, but
Well.
we don't have to do that now.
So, okay, now, I mean, I can do that quickly here. Are you okay? I mean, I didn't do the computation, but if you work out the formula for this, you realize that it's in K. And what's going to be important is that K commutes with everything in the algebra. If you write what this means, yes, okay. Well, let's actually do it. So if you use the anti-commuting property, you get this. Now you get a reduced norm in the middle. And now you make this one commute to here, for instance, and then you get the other reduced norm. Okay, other questions? So now we're going to move a little bit to arithmetic properties of Quaternion algebras. This was just over a field, and now we're going to move to number fields and local fields. Okay, so definition is going to be as follows. So now we take K, a number field, and we are going to consider the local behavior of a Quaternion algebra over K. So A equal K. And so that will take V a place of K, meaning explicitly either a real or complex embedding of K up to conjugation, or a prime ideal of the ring of integers. And so we have a corresponding completion, KV, which is either here or C, like the completion of the image, and here the associated p-adic completion. And so we say that V is unramified in A if when you extend the scalars to KV or K, well, just for explicitness, I will say, like, if A is AB over K, then this extension of scalars is just, you take the same A and B, you see them as elements of KV, and you just consider this algebra. You just change the coefficients to KV. So unramified, if that's isomorphic to the 2x2 matrix algebra, and we say that it's ramified, otherwise meaning that this is a division algebra. So in A, let's write it explicitly, if this is a division algebra. Okay. And so why did we introduce this notion? Well, it's going to play a role later because the properties are going to be different at ramified places and unramified ones. But at first, one thing that it gives you is actually a complete classification of Quaternion algebras up to isomorphism. That's the following theorem. The following is a bijection, so we have Quaternion algebras over K up to isomorphism. And on the other side, a finite set R of places of K with even cardinality, so size of R even. And the map being you send an algebra to the set of ramified places, which I will write ram of A. So this theorem is really saying four things. First, the set of ramified places is finite. Second, the set of ramified places has even cardinality. It says that the set of ramified places completely characterizes the algebra up to isomorphism. And it says that every finite set of even cardinality can be realized by some Quaternion algebra. Okay, so this is saying these four things at the same time. Yes? Oh, the cardinality, the size. Yes. Other questions? So let me give you an example maybe of this. So if we take A to be -1 over Q, so what is the ramification set of A? Okay, so we already said that over R, this is a division algebra. So definitely it is ramified at infinity. And so because the ramification set has even cardinality, we must be missing something. And there's another result saying that if a if a prime is ramified, then it has to divide either 2 or one of, the numerator or denominator of A or B. And so in this case, we just have -1, so there's no numerator or denominator. So the only thing that is left is 2. And in fact, you can check that it is indeed ramified at 2. So that's the ramification set of this algebra.
What is that division algebra?
The over Q2? Well, it's it's -1 over Q2.
That doesn't have like a nice description like the Hamiltonian.
Well, that's probably the nicest one you can find. But in general, okay, for QP, okay. So something I didn't say, but you may want to know is that over every local field except C, there are exactly 2 isomorphism classes of Quaternion algebras. The 2x2 matrix algebra and 1 division algebra. And you can be fairly explicit about it for QP. Okay, let's see if I can get this right. I think you take U in in ZP cross that is not a square. And you should take, I think it's minus U and P, and that's your division in general. So this is not quite this shape, but you can turn it into that shape. It's isomorphic.
You said it's not a square.
Yeah, no, I said not a square. I didn't write it, yes. Questions? Yes?
So here in the finite sets also include the empty set, right? Which is
Possibly.
trivial matrix algebra.
Exactly. Yes. The matrix algebra. So for the 2 matrix algebra, you just like all of these will be the 2 x 2 matrix algebra. So you get the empty set here. Yeah, that's right. For the if you take the two. If you take 1, 1, for instance, yes, 1, 1, giving them the 2 x 2 matrix algebra here, then all the places are unramified, and that's the only one. Other questions? Okay, so to say a bit more about the arithmetic of quaternion algebras, we need to introduce orders. So it's going to be my next definition. So an order in A is a subring O inside of A such that if you extend the scalars, you get the whole algebra back. And O is finitely generated as ZK module. So that's an integral structure in A, an integral form of A.
What do you mean by ZK?
Sorry, ZK means the ring of integers of K.
So K is a number field.
Yeah, K is still okay. Yeah, now K is a number field. Yes, okay. K number field.
You said it in that definition.
Yes. I didn't say that that this setting would go on, but yes, this is over a number field. And so yeah, that's the ring of integers. Okay, so examples. Well, maybe the simplest example in the is in the matrix algebra. If you take M2 of the ring of integers inside of A, which is 2 x 2 matrices, then this is an order. So we can check the properties. It is a subring, yes. If you extend the scalars, you get the whole matrix algebra, yes. And it's finitely generated as a ZK module. In fact, it's actually free over rank 4 over ZK. And okay, maybe over more general quaternion algebras, if you take if A and B are actually integers, then O equals K plus Ki plus Kj. Whoops, I meant integral coefficient plus Zk Ij. That's also an order. So again, we check the properties. It's a subring. This is not very read. Can you read this? Yes. Because we chose A and B integers, when we multiply the scalars that come out are still integers. So this is a subring. If you extend the scalars, yes, you get everything. You just, because extending scalars, you will just get the whole of K here and here. And it's finitely generated as a ZK module. I just wrote it by finitely many generators over ZK.
So do you mean ZK times I, or do you mean Z of Ki?
Yeah, okay. Rewrite. Yeah, and just take integers as scalars. So yeah, I'll rewrite it. Plus ZK times I plus ZK times J plus ZK times this way. Okay, and just one piece of terminology. We just say that O is a maximal order if it's maximal for inclusion. That is, if there is no order strictly containing it. So maximal orders play in quaternion algebras the role that the ring of integers plays in a number field. But there is a subtlety, which is that maximal orders are not unique. There might be several maximal, there are always several maximal orders. So they're not unique, and one way to see this is that you can take one maximal order O, and you can conjugate it by some element in A. That will, you can check that conjugating preserves the property of being an order and also of being maximal. And you can also check that you really do get infinitely many this way. By looking, for instance, at like the common denominator of elements in there, you can see that they are not the same if you choose X appropriately. But, so that's infinitely many maximal orders, but there are only 5 orders up to conjugation. Well, okay. I mean conjugation in this sense, not in the sense of the bar operation on quaternions. Yes, that's a bit of an ambiguous word. It's also the same as saying up to isomorphism in that sense. Here, isomorphism of rings, of ZK algebras.
Is this a statement only for quaternion algebras, or is this a statement, an order, and definition for all algebras over a number of fields?
You mean, well, this definition makes sense for any algebra. The thing is, for some algebras, there might not exist a maximal one.
Like if you just take Q itself, you don't have a maximal order, right?
You do, it's Z.
Well, can't you take Z and then also take all the halves?
Yeah, that's so. If you want to make it subring, you'll have to add all powers, all inverse powers of 2, and then it's not going to be finitely generated over Z. So if for your algebra you take a number field and you see it as being over Q, then orders are finite index subrings of the ring of integers, and the unique maximal order is the ring of integers. Okay, and so there's only finitely many maximal orders up to conjugation, and we can be a bit more precise in the case that will be of interest to us, namely we have the following theorem on Eichler. So we'll assume that there is one infinite place that is unramified. An unramified infinite place. So, okay, maybe one thing I didn't mention, complex places are always unramified because quaternion algebras over the complex must be 2x2 matrix algebras. So this means either the field has at least one complex place, or among the real places, there's at least one that is unramified. Okay, so that's the condition. Then there is between maximal orders in A up to conjugation. And a certain class group. So I'm going to, certain class group of K. Just let me write it first and then explain what my notation means. And okay, so let me explain this. So okay, so this would be the usual class group of K, just fractional ideals modulo principal ones. I'm adding an A here, saying that I don't quotient out by every principal ideal, but only by the principal ideals that have a generator that is positive at every real place that is ramified, at every real place that is ramified in A. So doesn't matter what this is exactly, that's why I'm not writing it down, it's just a variant of the class group, okay? And then you quotient out by squares of all ideals, so this is going to be an elementary abelian 2 group, and you modify the primes that are ramified in A. Doesn't matter what this exact class group is, it's just something that is mostly in terms of K, even though it sees the ramification of A. It's a certain class group, it's finite, and it's quite explicit compared to like this set of maximal orders, which is kind of complicated. So yeah, the exact thing doesn't matter too much, but I just want to emphasize that it's a certain class group, and I'm going to call it C of A for now, and the precise definition won't matter too much. Yes?
Do you expect it to contain the regular class group of K, or the other way around, or neither?
No, because so if you forget about this and you add this extra condition, the positivity condition, then it's an extension of the usual class group, but then we take a quotient. So it's a quotient of an extension.
So if you took A, like if you take KQ and AQ.
If you take KQ and A, well, okay.
Or any number field, whatever, and the number field over.
Here A should be a Quaternion algebra. So yeah, if you take. Yeah, maybe the basic example would be take A, the 2x2 matrix algebra. Then you can forget about this A here because there's no real place that is ramified. So it's just the regular class group. There's also no prime that is ramified. So then it's just the usual class group mod squares. Yeah, that's.
Sorry, you just said this is only true for Quaternion algebras A.
Yeah, there's a variant for some other types of algebras, but yes, the way I stated it, it's for Quaternion algebras. Other questions before I go on? Okay, so from this setup, we can now create an arithmetic group attached to Quaternion algebras. So as a notation, I will use RS as the signature of K, meaning, again, the R is the number of real embeddings of K, so same as real places. S is number of pairs of conjugate complex embeddings. And I'm going to write U as the number of unramified real places of K. I'm still, so okay. So K is still a number field and A over K is a Quaternion algebra. Right? I'm keeping this in the background. And so let X be a product of U times the hyperbolic plane and S times the hyperbolic free space. And I will define, so I will also take O an order in A, for now not necessarily maximal. And I write gamma of O to be the following quotient, take the unit group of O, and I'm going to mod out by scalars. It's going to be slightly better because I want to make it act on that space, and these scalars act trivially anyway, so I'm just modding out directly by this. Oh, and I'm going to add a small extra thing, which in some cases is not going to really play a role. I'm going to add a plus here. Yes. Reduced norm should be positive at every real place. Every real place. It's not really necessary. We can do variants where we don't put that condition, but for this setup, I'm going to put that condition. And I want to see this in PGL2R to the U times PGL2C to the S, sorry, plus, meaning positive determinant. And so how do I see it as a subgroup of this? Well, I just embed it diagonally using all the unramified real embeddings and all the complex embeddings. Okay, so this way I embed this group inside of that. So that's an example of an arithmetic group in the sense, in the general sense that Paul defined yesterday. So you can check, I mean, maybe it's actually easier to check it without this quotient, because then saying that this is an arithmetic group is essentially the same, and without the plus, I guess. This is the same as saying that multiplication in O is given, is given by polynomial formulas with integral coefficients, basically. Taking these quotients also makes an arithmetic group. So that's the arithmetic group attached to O. And I'm going to also attach, that's actually a definition here. And I will define y of O to be the quotient. So this acts on X by each factor, PGL2 plus acting on here, PGL2C acting on three-dimensional hyperbolic space. And so I can form this quotient. And I will call this an arithmetic, manifold or bifold, because really you could have singularities. Or bifold. Yes. So as a special case, if you take, for instance, the 2x2 matrix algebra over Q, and you take the 2x2 matrix ring over Z, then you just recover PSL2Z acting on hyperbolic plane. If you take an imaginary quadratic field and the 2x2 matrix algebra again, you get the usual, the Bianchi groups that you saw with Haluk. And you get plenty of other examples. Okay, so that's so that's the basic connected arithmetic manifolds I want to introduce, but it's actually important to not use a single order at a time for arithmetic, but a whole collection of them. So I'm going to use the following notation. Y, the disjoint union over all the conjugacy classes of orders. So I will parameterize them by ideals in my class group C of A of Y of OA. So we'll see in just a minute why this is important. Questions about this definition? Is this okay?
So this is a representation of an element in motion.
Yeah, I'm sort of, I mean, here I'm only using some kind of indexing of that set, but really there's a procedure to associate two various, I mean, I didn't really explain how you get this bijection between the class group and orders. So I'm sort of indexing it by ideals, but I'm not really telling you how you associate them. Just for keeping things a bit simpler, I don't give you the whole details of the construction. And I should say that, okay, maybe this looks slightly ad hoc, but there's a better way to view it, like which is to view it adelically. I'm not doing that, but really the best way to think about this is adelically. And the reason I'm doing this construction is because this is what we need to have the whole set of Hecke operators that we're interested in. So that's one of the main interests of arithmetic manifolds, is that they are not just manifolds or orbifolds. They have this plethora of operators on them that have arithmetic content, and these are the Hecke operators. So let me explain how Hecke operators appear in this context. So for SL2Z, CA is just the trivial group, so there's a single one. For Bianchi groups, it depends on the class group of the field. So if the class number is odd, there's a single thing, because you mod out by squares, you kill everything. If the class number is even, then there will be several components. Yeah. So this thing is disconnected. This is the disjoint union. This is a disconnected manifold. Yeah. Okay, so let's find Hecke operators. So I'm going to take two lattices in general in G. Yeah, okay, let me write G for this group so that I don't have to write it all the time. Yes. And so we have X mod gamma and X mod gamma prime. And we would like to create something that goes from here to there. And note that these two are not necessarily the same. So there will be some kind of permutation of the components going on here. And you take delta, some element in G, which is going to have to satisfy some properties with respect to this, the diagram I'm about to draw. And so you can take the following, okay, which direction did I want to conjugate this way? You can take gamma, intersect it with the delta conjugate of gamma prime, and that's going to be something covering this. And I'm going to assume that this is finite. a finite map, meaning that's the same as saying that this group has finite index in that one. And if you map x to delta x, then you land the other direction of the conjugate this way, which is a covering of this one, and I'm also going to assume this one is finite. And now what is the Hecke operator on, well, points? So you take a point here, you take all of its pre-image here, so you get a finite number of points. You push them through this map, which is, in fact, this is an isomorphism. And then you push them down to here. And this whole composition is what we call the Hecke operator. So I'm writing it as a dashed line because it's not an actual map on points. It sends one point to a finite collection of points. But because of that, you can make it act on anything linear attached to these spaces. Like you can make it act on functions, homology, differential forms, whatever. Everything that's linear, you get an actual linear operator this way. Okay. And in our arithmetic setting, we will take gamma, which is some gamma of OA, gamma prime, which is gamma OB, and delta is going to be an element of our Quaternion algebra, which we also see as an element of G through the same embeddings as before. And I'm going to assume that when you take the reduced norm of delta times the ideal A, I get P times B for some prime ideal. And then, in this case, I'm going to call my Hecke operator T sub P. And these are the ones that we want to look at for arithmetic. And so, so these TPs will go from from y of OA to y of OB. And so, if you put all of these together for all the A's and B's, you get an action of this TP on the whole y of A. It's going to permute the components. And how do you know which components are which ones? You just look at multiplication by P in the class group, and that tells you what permutation you get. Okay? And I'm going to write bold T with the algebra generated, well, I could say the ring generated by the TP for, well, okay, for P unramified in A. You have to be slightly careful for P defining A, for P ramified. So let's assume that it's not. Okay, questions about these definitions? So now we've defined arithmetic groups and manifolds attached to quaternionic orders and quaternion algebras and the Hecke operators. And now I want to talk a bit about algorithms to compute all of these objects.
In which
Yes.
way is this an algebra? Do you take the free algebra?
Just the free commutative algebra on that, and then I'm going to make it on various things. Yeah, yes, okay, yes, commutative, free commutative algebra on these. The point being that once we're going to make it act on the good objects that we're going to consider, they're really going to commute. Okay, so algorithms. Okay. So I'm going to go to the three-dimensional case. So x is just h3. So this means that so u equals 0 and s equals 1. And so to compute so we want to compute, so for computations, we need some kind of nice model for x mod gamma, so some way of representing x mod gamma. And the way we're doing this is by using a fundamental domain. So what is a fundamental domain? So I'm actually, going to skip the general definition, but we're going to see an example immediately. So essentially, it's a nice set of representatives of the quotient of x mod gamma up to the boundary. If you don't know what this means, just wait for a second. Think about essentially a set of representatives of this quotient. So that essentially means pick a point in each gamma orbit. So we need to find a procedure to pick a point in every gamma orbit. And the way we're going to do it is by using the distance. We have a hyperbolic distance on H3. And so we can do the following. We will choose a center C inside of X, any point so far. And then in each orbit, so you look at an orbit, you'll have X, gamma X, etc. So the whole orbit of X. We need to pick a point in that orbit, and we're just going to choose the one that is closest to C. That seems like a good way of picking an element. So closest one, we choose this one. So we do that for every orbit. And so what is the set that this produces? I will write it D sub C of gamma. This is going to be a Dirichlet domain. So by definition, the set of x's in X that are the closest to C in their orbit, such that D of gamma X C, well, the other points in the orbit are further from C than this one. So for all gamma in gamma. Okay, so we'll see what this actually looks like. Are there questions at this point? Sorry?
So it's like soap bubbles expanding around those representatives and then...
yes, that's, yeah. That's a way to think about it, yes. So it's like when you expand a bubble around the center C, then you're going to stop when it touches the other points. That is, yeah.
I was thinking of expanding around the gamma.
The orbits.
And then each.
Oh, the first one that touches
in one of those bubbles.
Yes, right. That's also, yeah, okay. Let me draw a few more pictures of, yeah. Yeah, then you don't have a unique representative in that set. So, but that's okay for a fundamental domain is not quite a set of representatives, so we allow some doubles like this, but that will only happen on the boundary. So that's going to be the important thing. Well, yeah, we'll actually the structure of this. And I should say that this actually works only if the stabilizer in gamma of C is trivial. Otherwise, it's actually not a fundamental domain. We'll see also in a little bit why that is. So maybe to get a picture of this, let's look at one of these inequalities. Distance from gamma x to C is greater than distance from x to C. Now, the distance is actually preserved by the group action. So this is the same distance from x to gamma inverse C. Okay? Now, why is this important? Now that I've written the inequality like this, I can focus on gamma rather than on x and look at the set of all x's that satisfy this. And what is that? You take C, you take gamma inverse C, and you want all the points, all the x's that are closer to C than to gamma inverse C. So it's going to be separated by a bisector like this, and I'm just taking the half space on that side. And then I can take another gamma, and I'm going to cut out another bisector like this, and then another one. So the upshot when you do this is that the Dirichlet domain, which is the intersection of all of these, it's actually a polyhedron. It's like it has faces. And the point is that these bisectors in space, they are very nice. They are geodesic surfaces. So let me draw what this is. If you were to do this construction in an arbitrary symmetric space, bisectors could look really ugly. But here they are very nice. So hyperbolic free spaces like this, you have this plane is the upper half space above that plane, and they are either half planes that are orthogonal to the plane here, or half spheres again that are orthogonal to here. So you get the sides of this domain are pieces of things like this.
And a line that intersects these orthogonal planes can be arbitrary.
These ones?
Yeah.
Yes.
Yeah.
Okay, so I'm going to be short on the end of this, but yeah, what I should say is that once you have one element with gamma here, then you automatically get also the inverse on the other side, and gamma sends this face to that face exactly, and x mod gamma is exactly this domain when you glue these faces according to that pairing. That gives you exactly x mod gamma. So in that sense, this domain really is a model for x mod gamma. And so having a Dirichlet domain like this is sufficient for computations with the group, its homology, its Hecke operators, and everything. So briefly, I want to say a few words about algorithms to compute these Dirichlet domains. So okay, maybe a few points about Dirichlet domains is that if gamma is, so if x mod gamma has finite volume, oh, sorry, I actually missed something. Yes, something I should have said here is that these have finite volume. That's actually and compact if and only if A is a division algebra. I'm sorry. That's very important. So in most cases of Quaternary algebras, division algebras, you get a compact quotient. Yes. Okay, yeah, so I could just leave. Okay, we could take a break now, and I say a few more words about algorithms in the second lecture, and then I'll do a bit less of the theory. That might actually work. Yeah.
You can finish whatever you want to say now, and we take a 15-minute break whenever you're done with it.
Actually, I'd rather say more about the algorithmic part and just skip a bit more of the theory in the second part. So maybe it's good to take a break now.
Are there any questions before we?
Yeah. So let me just finish my sentence. If it has finite volume, then dp of gamma has finite size. That's going to be important. I mean, well, let's call them faces, maybe dimension 3. Yeah. So okay, let's take a break now. Are there questions at this point?